Hello everyone and welcome to Control Engineering and Robotics tutorials. In these tutorials we present real and applicable knowledge of control engineering, robotics, machine learning, computer vision, optimization and applied mathematics. In this robot operating system or ROS tutorial you will learn how to model robotic systems by using Xacro. The word zacro is written as Xacro, and some people pronounce this word as zacro. However, some other people pronounce this word as xacro. However, I will use the first pronunciation, that is, I will pronounce this word as zacro. Okay, so what is Xacro? Xacro is a macro language for XML. With Xacro, we can construct shorter and more readable XML files, that is, XML URDF files, and we can perform math operations in our URDF file. Some of you might stop me over here and ask me the following questions. What is a URDF file and how to model robots by using the URDF files? Well, I cannot explain everything in this video. For those of you who are not familiar with robot modeling by using the URDF files, I created a separate video. And you should watch that video tutorial before watching this video tutorial. A link to that video tutorial, that is, to the video tutorial that explains how to model robots by using the URDF files, is given in the description below this video. Here's a brief lecture outline. The whole purpose of this video lecture is to teach you how to combine Xacro with URDF files when modeling a robotic system. More precisely, in this video lecture, you will learn how to clean up, parametrize and simplify URDF files by using Xacro, which is a macro language for XML. Then, you will learn how to write a launch file that uses Xacro files. And finally, you will learn how to visualize and simulate robotic model and system in RViz. By the end of this video, you will be able to generate this nice animation and you will be able to simulate this robot. To capture your attention as early as possible and to make this video tutorial as interesting as possible, here is the Xacro files that completely parametrize and models the robotic system that you can see over here. The robotic system consists of two joints. The first joint is placed over here and it's a rotational joint. The second joint is placed over here and this joint is a translational joint. Now, if you go back to the URDF file, you will see that everything is parameterized over here. For example, here's our base link. Here's the first link and here's the second link. The geometrical parameters of these links are shown over here. Summarize, by the end of this video you will be able to write this file from scratch and to understand how to use Xacro. Then you will also learn how to write this launch file that's used to visualize the system in RViz. And finally you will learn how to actually launch RViz and how to visualize the model. But before I start, I would like to mention the following. It took me a significant amount of time, energy and planning to create this completely free video tutorial, as well as almost 300 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Okay, let's start. The first step is to install or to verify the installation of RViz and other packages. The best way to actually verify installation is to try to install a package. So let's do that. Let's try to install RViz. Open a terminal and in this terminal type this command. Let's see what happens. Okay, we can see that in my case RViz is already installed. However, in your case you might see the installation progress. Perfect. Let's proceed. Let's test RViz. To test RViz, we need to open a new terminal and we need to open or initialize our ROS core. Okay. RViz is a simple node in the system, and that's why we need to start our ROS call, which is a ROS master. Then, in the original terminal, you need to type this command, ROS run RViz, and let's see the response. And voila, here's my RViz. So RViz works perfectly. So far, so good. Close RViz, and let's proceed. Next, we need to install several other packages. We need to install the package for URDF file modeling. And you need to type this. Let's see what happens. Since I updated my system, it's going to take some time to actually install this package. However, the package was already installed. It's just being updated. Okay, let's now install the package for Xacro. You need to type this command. Okay, Xacro is properly installed. Then, here is the optional thing. If you want to check the URDF file, then you can install this nice package. However, in this video I will not be checking the URDF files. The next step is to create our workspace and to create the Catkin package. Consequently, we need to follow the standard steps. First, I need to create our folder and subfolder that will contain our package. Then I need to run catkin make. Let's do that. However, let's first see where we are. Okay. Let's create our two subfolders and let's go to our root folder for our package. It's completely empty. Next, we need to run catkin make. Okay, let's see the output. Let's go to source. Here in source, we need to create our package. To create the package, we need to do a few things. First of all, we need to source our setup bash of our new workspace. To do that, we need to execute this command. Okay, let's verify the path and that our environment is properly sourced. Here you should see something like this. This is our package and this is the source file. So far so good. Let's create the package. To create the package, we will be using this command, catkin create package. Then we need to specify the name of our package. In my case, I'm calling the package robot model package. And over here, we need to specify the dependencies. The dependencies are ROS sub-packages that will be included in our original package. That is, in the package that we'll create. Here, I'm using the following sub-packages or the dependencies. ROS CPP is environment for executing C++ files in ROS. TF2 is a package that lets the user keep track of multiple coordinates frames over time. It's a very useful package. Geometry messages is the package for messages and for common geometric primitives such as points, vectors, and poses. URDF is the package that enables us to write URDF files. RViz is the RViz package, and this package is used to enable us a graphic user interface tool for setting up and publishing joint state values for a given URDF files. And finally, we need to include xarco. Okay, Xacro, better to say. Let's run this command and let's see the output. Okay, so far so good. Let's see what happened. Over here we can see a new folder, and that's our package. Let's go to that folder. It's completely empty. Actually, it's not. We have 4 files. We need to create 2 folders. The first folder will contain our Xacro file, and the next folder will contain our launch file. Consequently, we need to create these 2 files, or these 2 folders. The folder for storing the URDF file, and the folder for storing the launch file. Perfect. Next, we will create 2 Xacro files. This is the first one, and this is the second one. The first one, called materialcolor.zacro, will be used to specify the definitions of material colors that will be used during our simulations. And the second file, called robot.zacro, will actually include this file and the parameters from this file, and this file will be used to specify the robot geometry. Let's first create this file. To create this file, we need to go to the folder URDF. Consequently, you need to change your current folder. And in this folder, let's create the file. Here it is. It's completely empty file. To make this video tutorial as short as possible, I will simply copy and paste the script from the previous file to my new file. And I will explain this script. Over here, we are specifying that this is the XML file. Here we start robot environment, and here we end the robot environment. This file will define the colors. I'm specifying material, name is black, black is the name of the color, and over here we're specifying the color. RGB stand for red, green, and blue. And the A is the transparency. Since the color is black, we have 0 for red, 0 for green, and 0 for blue. And the transparency is 1. That is, it's completely non-transparent color. Okay, here's the definition for blue color. We have 0, 0, and 0.9. Here I don't want to specify completely 1. I specify 0.9. And over here it's 1. That is, the transparency is equal to 1. Similarly, we define green, red, and white. And that's our material file. Let's save this file. Here you can see the power of Xacro. We can write a separate file, and in that separate file we can define some parameters or material properties or some geometrical properties. And later on we can import that file in our original file that will define the geometry of the problem. Consequently, let's create the file that will define the geometry of the problem. Close this file, and let's go back to the terminal. Let's verify that the file is actually created. It's given over here. And let's create our main file. This file, called robot.zacro, will contain the parametrized geometric description of our robot. And again, in order to make this video short as possible, I will simply copy and paste different pieces of the code to this file, and I will explain it. Before we write the Xacro file, it's a good idea to sketch our robot. And here is the two-dimensional representation of our robot. First, I will sketch the base link. Here it is. Then, on top of this link, I have another link. Here it is. And finally, I have the second link. It's on the top. This link will be called as base link. Then this link will be called first link. And this link will be called as second link. Then we have two joints. Between the base link and first link, we have joint 1. Then between the first link and the second link, we have joint 2. The first joint, that is joint 1, is a rotational joint. Joint 2 is a translational joint. The rotational joints are called revolute. The translational joints are called prismatic joints. Next, let's create our Xacro file by keeping in mind this important sketch. Over here, I will simply copy and paste a piece of code from the file that I previously created. And let's explain this code line by line. First of all, we need to specify that this file is the XML file. Then we need to specify that we are actually using Xacro macros. We can do that with this line. And here we need to define the model parameters. But before we do that, it's very important to go back to this line and mention a few things. First of all, we need to specify the name of the robot. I call it as simple robot. And over here, you need to close the environment. And that's very important. And by looking at my original file, you will see all the way down this environment. That is, the robot environment starts from here and ends over here, and you need to close it, and I will close it at the end. Our next task is to specify the parameters that uniquely define the base link. The base link is a cylindrical link, and obviously two parameters specify its geometry. The first parameter is the radius of the link, and the second parameter is the length or the height of the link. Let's specify these parameters by using Xacro. Here they are. We start by opening the environment Xacro, then we specify the property. We give the name of the parameter name is base link length, and we specify the value. Okay, next we specify the radius in the same manner, and we give the value of 0.2. Let's look at our first link. Again, the first link given over here is a cylindrical link, and it also has a radius and it also has a length. Consequently, let's specify these parameters. The name of the parameter or the property is first link length, here's the value, and here's the first link radius. Okay, how about our second link? Here's our second link. It's a prismatic element, and we need three parameters to specify its geometry. We need its length, height, and width, and consequently, over here we specify second link length, second link height, and second link width. Next, let's define the parameters of our joints. We have two types of joints. We have rotational or revolute and prismatic or translational joints. We need to specify the upper and lower bounds for the rotational angle, and these bounds are defined over here. These values for the bounds are given in radians. Then, For rotational joints, we need to also specify maximum revolute velocities in meter per second, or better to say in radians per second. Here I assume 3.14 radians per second. And we need to specify max effort, and max effort is not an important parameter for the time being. Just enter a relatively large number, for example 300. Similarly, we need to specify the limits, velocities, and the effort for our prismatic or translational joint. And here are the limits. We assume that this joint can go from 0.5 meters to minus 0.5 meters with a maximum velocity of 0.8 meters per second, and this is the maximum effort. Next, we need to tell to our compiler to include the information specified in our material color file. Consequently, we need to use this code line. This code line will simply include the content of this file inside of the file. It's very important over here to specify the correct relative path to our file. We know that it's in the folder robot model package. The subfolder is URDF and the name of the file. Okay, next let's define our base link. To define our base link, let's again analyze this figure. We define the parameters of this base link, namely the radius and the length, and we need to tell to our compiler to properly interpret these dimensions. First of all, we need to open the link environment and close the link environment, and inside we need to give the name to our link. We call the link as base link. Over here we define the visual representation of our link, and over here we specify the geometry of the link. We specify that the link is of a cylinder type, and we need to specify the length. The length is given over here, and this is very important. Here is how we used the previously defined parameters. So if you go back, you will see it over here, base link length, and we can also see it over here. Perfect. Then we need to specify the radius, and again we use the parameter base link radius. Next, we need to specify the origin. The origin is specified like this. R, P, Y represent roll, pitch, and yaw, and X, Y, Z represent the offsets. That is, this is rotation, and these are the offsets. We set the rotation to 0 and the offsets to 0. And over here we specify the material name, it's blue. And this blue is actually defined in this file. Here it is. Blue, 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 blue is here. So instead of typing blue, a more longer version would be like this. However, we don't want to do that, and that's the power of Xacro. We can simplify and we can significantly decrease the length of our URDF files. Next, we need to specify and define our joint 1. Let's do that. Here's the definition of joint 1. The name of the joint is joint 1 and the type is revolute or rotational joint. And here we need to specify the parent and child links. Let's go back and analyze this figure. The parent link to our joint 1 is obviously base link. Here it is. This is the parent link, and the child link is the first link. So let's specify that. Here, base link, parent link, child link is the first link. And note over here that we still didn't define the first link. We will define it over here. Next, we need to specify the origin. X, Y, and Z positions of the origins are 0, 0, And what happens over here? We see that this joint should be displaced for this amount with respect to the coordinate system of our base link. Let's analyze this. Here it is. The coordinate system of the base link is actually placed over here. And let's sketch this coordinate system by changing the color. For example, let's use the green color. Here it is. Now, we are saying that the coordinate system of our joint should be placed over here. And let's change the color. For example, let's use this color. And here it is. This is the coordinate system of our joint 1. It has an offset graphically represented over here. And this offset is actually equal to half of the length of our base link. And that's precisely what's written over here. And again, notice the power of Xacro. We can use mathematical expressions for defining the offsets. Then we need to define the axis of our joint. Obviously, this joint will rotate around the z-axis, and the axis is then 0, 0, 1. And over here we specify the effort, we specify the velocity, and lower and upper bounds. All these variables are equal to the parameters that are previously defined. Okay, that was our joint 1. Let's proceed and let's define our first link. Here's the definition of the first link. We start the link environment and we close the link environment. The name of the link is first link, and here we define the visual representation of our link. Here we define the geometry. It's a cylinder. We need to specify length and radius. Obviously, the length of the cylinder is equal to the first link length, and that's the parameter defined over here. And the radius is also equal to the parameter. Next, we need to define the origin. And here you should stop for a second and carefully watch what I will explain in the sequel. Notice over here that the origin is displaced. And as you can see over here, we have 0, 0, first link length over 2. So what's the catch over here? If we didn't add this offset along the z-axis, we will have the following scenario. Here is the coordinate system of joint 1. I will represent it over here. If this parameter over here, that is this offset, is equal to 0, then our first link will be actually placed like this. Let me change the color and let me sketch it. Its center will be at the 0 point of joint 1. That is, we will have the following scenario. First link will be centered precisely at the coordinate system of joint 1. However, we don't want to do that. We need to specify the offset of the first link with respect to coordinate system of joint 1. And I need to erase this part. Need to increase the size of my eraser and to explain you what you actually need to specify. The correct definition is the following one. Again, here is the coordinate system of joint 1. We want the following scenario. We want our link to start precisely from the 0 point of the coordinate system of joint 1. That is, we want to have this case. This means that we need to offset our link 1, that is, its center, with respect to the coordinate system of joint 1. And this offset is obviously equal to half of the length of our link 1, that is, of our first link. And that's precisely what's happening over here. We are saying define first link and then offset the first link for this distance with respect to the coordinate system, that is, the center of the coordinate system of the first joint. This is very important to keep in mind. Next, we need to define joint 2. Joint 2 is a prismatic or translational joint, and let's define it. We start the joint environment and we end the joint environment. We need to specify the parent link and the child link. Let's look at the picture. The parent link is the first link and the child link is the second link. And we write parent link, first link, and child link, second link. Then we need to specify the origin of joint 2. Again, what's happening over here? The origin will be displaced. However, the main question is, with respect to what coordinate system we are performing this displacement? The answer is, this offset is made with respect to the center of the coordinate system of joint 1. And let's look at the picture. Here is the joint 1. And we need to specify the displacement. That is, we need to put a coordinate system of our joint 2 over here. What is the displacement of this coordinate system with respect to the coordinate system given over here? The displacement is precisely the length of the first link. And over here, we actually specify that. We're saying that the origin of the second joint, or its coordinate system, is displaced for the length of the first link with respect to the origin of the first joint. And over here we specify the axis of our joint. The axis is obviously y direction. This is because we perform translation in this direction. We can go either in this way or in this way. And this is the y-axis. And finally, let's define the second link and let's close the environment. First, let's close the environment. And again, double check that you started the environment over here and that the environment is actually closed at the end. Here's our second link. Start the link environment and the link environment, define the visual, and define the geometry. The geometry is a box. The box is defined by width, length, and height. And here are the sizes. Second link width, second link length, and second link height. These are the parameters defined at the top of this file. Next, we need to define the origin of the link. There is no rotation. However, again, we have translation. Following the same principle, we need to define the offset of the coordinate system of our second link with respect to the center of the coordinate system of its previous joint. And its previous joint is joint 2. Obviously, we will have displacement or offset in z direction for the half of the second link height. Let's illustrate that. We're saying that we want to place the coordinate system of the second joint exactly the middle, or actually of the second link. Again, I need to correct myself. We're saying that we want to place the coordinate system of the second link over here, that is, at the center of the second link. And consequently, we have this displacement, and this displacement is exactly 1/2 of the height of our second link. And that's it. Next, we need to save our Xacro file and close it. Let's go back to the terminal and let's verify that we actually have two files. Perfect, we have material and a robot file. The next step is to define the launch file. The launch file will be used in order to start RViz. Go to launch file folder, and over here we need to create our launch file. The name of the file will be robot xacro.launch. Here it is. And again, I will simply copy and paste the code that I previously wrote. Let's explain the code. First, we need to tell that this is the XML file. Then we need to define our launch environment by opening launch and closing launch. And over here, we need to specify this parameter. We give it a name, robot description, and we need to execute this command. This command will execute this script called Xacro with this argument. And the argument is our Xacro URDF file defining the geometry and all the parameters. Over here we specify the relative path to our file. Perfect. This is the first step. The second step is pretty much standard, and I explained this step in my previous video tutorial, whose link can be found in the description below. We need to include this package, joint state publisher, graphic user interface, and we need to include this node or this package, robot state publisher. Finally, we need to specify some parameters of RViz. First of all, we need to include RViz, and we need to specify this parameter. This file will not exist the first time we start our RViz. Later on, we will create this file by simply saving the configuration of RViz. This file is used such that we can save the configuration, and every time we start RViz, we will start from the same configuration, and we don't need to spend tremendous amount of time always configuring our RViz. Okay, that was our launch file. Let's save the launch file and let's close our gedit. Let's see the launch file. Here it is. Perfect. Next, we need to rebuild our environment, and we need to go to our original workspace folder, and we need to type Catkin make. Okay. The final step is to launch our launch file. However, before we do that, we have to make sure that ROS core is still running. This is because RViz is simply a node, and in order to run a node, we need ROS core. So ROS core is running in the background. If it's not running, you need to reopen it by typing ROS core in the separate window. Let's see how to launch our RViz. To launch RViz, we need to use this command. We specify the command ROS launch, we specify the name of the package, robot model package, and we specify the name of our launch file. Let's do that. And let's hope that everything will work as expected. Perfect, no errors. However, we see something over here, or we don't see anything over here. Well, we don't see our robot. We're expecting our robot over here. So why is that? For two reasons. First of all, over here, we need to add our robot model. Click on OK. Voila! Here's our robot model. And we see a simple problem over here, which we will correct in the sequel. And we need to specify over here that fixed frame is based link. Here it is. And voila, here it is. by saying that the fixed frame is base link, we actually created all the offsets in the correct manner. The next step is to verify that we can actually move our robot. Consequently, over here, we have this window, and we can see that the node joint state publisher graphic user interface is running, and this node will enable us to move our robot. And if you remember, in our launch file, we included this node. So let's see what happens. Joint 1, perfect. We can rotate, and joint 1 is here. Let's see joint 2, perfect. Before we end this video, we need to fix one thing. And to show you what we need to fix, let's go back and let's open our launch file. And let's see what is written in the launch file. Over here, I will go to my environment. It's under source. Here's our model, launch, and here's our launch. Notice over here that we have this file, robot.rviz. However, this file doesn't exist. So let's create this configuration file. Go over here, click on File, Save Configuration As, and we need to go to the proper folder. And we will save the file over here. The file name should be robot.rviz. Verify that this file name is correct. Robot.rviz. Let's see. Perfect. And click on Save. Let's close our RViz and let's go back to our terminal. Let's launch everything again, and voila! Next time we launch, the file robot.rviz will be automatically loaded, and we don't need to adjust robot model, and we don't need to adjust other parameters. However, there's one additional thing that we need to verify. We need to verify our coordinate systems. Consequently, click on Add and find TF. Here's TF. Here are the coordinate systems. So let's briefly inspect them. We can see a base link, we can see first joint, we can see a second link, and we can see the second joint. Perfect. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much.